The third method we're going to look at for applying multiple transformations to a single function is making a transformed table of values, or making a table of values for the new transformed function. Again, remember, as with all of the different methods we've looked at, that it's important first to factor so that the immediate coefficient of x inside the brackets is 1, and also to list the different transformations. So I've shown that here, the factored form and the listed transformations. Now, if you think back to the arrow method, which we talked about before, of applying multiple transformations, and I'll show that here, we applied each of the transformations in sequence, the reflections and stretches before the translations, and each of those were doing characteristic things. The vertical reflection was going to multiply the y values by -1. The horizontal stretch factor a half multiplied the x values by a half. The horizontal translation left of 1 subtracted 1 from the x value, and the vertical translation up 3 added 3 to the y value. Now, we can do all of that at once in a table of values. So let's look first at the vertical transformations. The vertical reflection is going to make the y values the negatives of whatever they were before, and the vertical translation up 3 is going to add 3 to them. So in the new function, we're going to have whatever the old y value was, and I'm going to use this y to represent the old y value. The new y value is going to be whatever the old y value is, negated because of this vertical reflection, and then with 3 added to it. So the new y value is going to be the old y value, this y being the old y value, multiplied by -1, and then with 3 added to it. And if you look back to the arrow method, that's exactly what we did to get the new y value. Now for the x value, which we're going to write in this column, to get the new x values of the new function, we're going to have to take the old x values and horizontally stretch them by a factor of a half. That means we're going to multiply each of the x values by a half, and then we're going to translate them left by 1. So to move them left by 1, we have to subtract 1 from their values. For example, if a point was at had an x value of 0, to move it left by 1, it would now have an x value of -1. So that half x minus 1 represents the horizontal stretch factor of a half being applied to the old x value, and then the translation of left 1 being applied to the old x value. Now, this allows us to work out our new coordinates from our old ones pretty quickly. So we just plug each of these values in for x here and for y here. So to give you an example, the first one, we have a half times -4, and that -4 comes from the table above, minus 1. A half of -4 is -2, minus 1 is equal to -3. Negative y plus 3 becomes -0 plus 3, which is equal to 3. Carrying on, half of -2 minus 1 would be -1 minus 1 is -2, and -4, again we're getting this from the next line down on the table above, plus 3. -4 is +4, plus 3 is equal to 7. So now we've got the point -2, 7 on this graph. And now I've filled in the rest of them by, again, taking the values from above, plugging them in for x and for y, and applying the different rules. Notice that it's important to work from the transformations that you've listed, because in the horizontal direction, if you looked at the original function, you might have mistakenly put a 2 there instead of the half. You have to work from the transformations that you've listed. Same thing with the horizontal translations. So these would be our new points, -3, 3, -2, 7, etc. And we could plot those now directly on the graph. Now, if you compare back to the other drawing, you'll see that you get the same result. And you should, using any of the 3 methods.